All right, buddy, good. Okay. So project, let me just move this out of the way. Okay, so project, my mic. Yeah, one more, but that one isn't too bad. No, no, we would never. Um, okay, project three. So if you're familiar with the knapsack problem, we're going to be doing a variation of that. That's actually a little bit simpler. So imagine you're given a fixed capacity bag and then a list of items of different weights. The goal for this project is to figure out how many different ways you can pack this bag without exceeding capacity. And with the knapsack problem, it's an optimization problem for like the value of each item that you put into the bag. But for this project specifically, we're just dealing with what is a feasible optimal packing. So we're just enumerating all the possibilities. So as per usual, you're given sample input and output files, in this case called p3.zip, to test your code against. So the input looks like this. We have a capacity and then followed by a list of um, item weight pairs. And your output will be a list or a list of lists. So for instance, for the first line in the input file, we have a bag of capacity 10 and then items sweater, book, skirt, glasses, shampoo with weights 9, 6, 8, 9, 6 respectively. And an example output is you would say in your output the capacity colon and then the capacity of the bag and then items to pack, and then this will be the final list of your solution. And if you notice, we have a list of a list. So the overarching list is the list of solutions, and then for each solution you have a list. And this list could either have a single item or multiple items if the capacity allows. So you can see here that um, we have a single list and then a single list nested within that. And this represents a possible packing. And then we're packing boots and pants. Does that confuse anybody? I know there's a lot of nesting. The one on the left here, boots and pants. Okay. And then for this other one, the bracketing is a little bit different. So we have our overall list and then two nested lists. And then one solution is to pack just the jacket, and the other one is just to pack an umbrella. All right. And then if you don't have a solution, then we return a list and then within that an empty list, meaning that there's no solution, obviously. Okay. So to run your program, as we talked about for when I went over Prolog, you just do swipeable and then your file name, input and output. And I'll go over debugging here, but basically you can debug your file if you do swipeable to enter the interpreter, load your file, and then do a trace, and then call the main function, and then you can step through the trace to see what all your functions are doing. I wouldn't suggest this for very involved input files. Maybe just try out simple one-line inputs and then see what your code is doing, because it kind of gets messy. This is a very recursive project. And then to disable the trace, you can do no trace. And then if you run main, then it wouldn't do a trace. It would just create your output file directly without you stepping through it. All right. So to be technical and exact, we're looking for ways to pack the item or permutations of items that are optimal and that are done without replacement. So what do we mean by permutation? So if since we're looking for permutations, if you can pack sweater and boots, and you can pack boots and sweater, those both count as two perfectly valid solutions, and your algorithm should produce both. So in permutations, the order does matter. And when we say optimal, we mean if you pack item A, B, and then the remaining items, if you put any of them into the bag, you're going to exceed capacity. That's an optimal packing. So for every list answer that you have, it should be the case that if we try to pack some other item that is unpacked for that packing, oh my gosh. If there's, for any solution that you provide in your list of solutions, if it's possible to find an item in the bag that can be packed into that packing and the capacity would still be good, then that answer is not optimal. So you want to basically push the limit of your bag until you can't find any more items that are feasible to add to that solution. And without replacement, and to put simply, that just means if you choose to pack some item, it's disqualified from being packed ever again until you begin a new packing. So if you pack A, then your next item better not be A. So basically no duplicates for that particular packing. And the input? No, that's a good question. You can assume the input is distinct. All right, so just to look at the problem space that we're dealing with. So we're going to have this really messy tree that's very complex, but this is the permutation tree of A, B, and C. So so for instance, if your first choice of item to pack is C, and here we're not worrying about the replacement part or the optimal packing. This is just all the solutions, all the ways that you can have a permutation. So, and the point being is that some of them are invalid. So we're going to start with the broadest thing that we can do, and then we're going to try to prune the tree to get optimal packings, because the optimal packings are just going to be a subset of all the permutations. Does that make sense to everybody? Okay, so this is a permutation tree for A, B, and C. So if you can see, if we choose C, then since we're not addressing the replacement policy just yet, you can choose C again. So in the C branch, you can choose C, B, and A. And then within the C branch of that, you can also choose C, B, and A. And the depth of the tree is related to how many numbers per packing. So we have 3 options for the first item. And then since we're allowing replacement, we have 3 options for the second item, and then another 3 options for the last item. So I put this diagram here to illustrate kind of the need for recursion in this problem. I hope it's apparent to you. So for each sub problem, we're still in this case, we're going to have like the same possible options. We're not dealing with pruning the tree just yet. So this is just figuring out all the possible permutations. And just to give a concrete example, so the original problem is to find all the ways that we can pack, basically we start by picking out an item, and let's say we pick C, and then after we made that selection, then we have another set of selections, C, D, and E, that we have to iterate through, but let's just say we choose C again, and then we have the same pool, which is C, D, and E. So this is one solution, and then we backtrack, and then we try C, C, D, and then we backtrack, and then the last call that we would make is C, C, and E, and then we backtrack, and then we're done with the C branch, since we've explored all the permutations that start with CC. So now I don't know why it points to E, maybe you should point to D, but let's just say the next thing that you would do is you go to E, and then the process would continue. So to look at some code for this, this is the permutation file that I posted. All right, so I really want you guys to understand what this code is doing. Your project is just going to be like adding more complexity to this, but this is to find all the permutations given a pool of items. So this iterator function, let's just step through it. So I'm going to enter the interpreter, and then I'm going to load the file. Do you guys remember last class when I covered Prolog? We had a member function that would iterate through all the items. I just went ahead and created my own version of it called iterator, just to be more verbose. But let's actually see what this is doing. You'll get singleton errors. That just means like basically in your parameters, you have variables that you have not used. So that's okay. All right, so we're going to do a trace and then dot to step through it. And then the thing that we want to test out is iterator. And then we're going to pass I think X is the variable that we're interested in computing. Yeah, okay. So X, so similar to member, it's just going to bind to all the elements in the list, but I want to use this as an opportunity to show you guys the trace and also backtracking. So just kind of reading the code. So we have two, if we have an empty list, then this function will just be false. But otherwise, we're going to end up having two branches. One is when we bind the head of the provided list to a solution. And remember, a bind is a base case. So we will have a value for x in this case. The other is we just skip it, right? So we have two decisions to make in this case. So here we don't bind because x will still be indeterminate, but we just call the subproblem on the tail. So when you make a query like this in Prolog, it's going to give you the first available option, and it's going to bind to 1, the very first element. But if you press space, you're telling Prolog, I'm not happy with this answer, and it's going to backtrack to give you a different solution. So what iterator did here is it chose this case here where it bound to the variable and it gave you the solution. So now, since you asked for a different response or a different value for x, it's going to backtrack. It's going to say, okay, now I'm going to skip this value. And then what it's going to do is it's going to bind to the next value. I'm just pressing space to step through, by the way. So it bounded to 1, but if I press space, it's going to redo it, and this time it's going to choose to skip the element instead of binding. So we're going to bind to 2 in this case. And then we get x is equal to 2. Two decisions, when you provide Prolog with backtracking, it's going to exhaustively search for all the basically true cases. And if I continue stepping through this, when it runs out of elements in the list, it's just going to return false. So it backtracked and it explored all the branches, and then it exhausted everything, and then it's false. So there's no more backtracking that can be possible because of this case here. So this is like terminal stop, no other possibilities possible. Does that make sense to everybody? Is there anybody here who it doesn't make sense to? Yes.
That caused the program to like fail and terminate?
No, false is like the last exhaustive thing that we do. From beyond that, there's no more backtracking. Yeah. I think it just calls it fail in the trace, maybe. Okay. So just as a side note, if I do that, it wouldn't really make sense in this case, but if I remove the false, then this is saying true. So all the base cases where you don't specify false are just going to be assumed to be true. All right. So let's put this method to use here in this function here. We are going to generate all the permutations, right? So we need some way to iterate through all the values. And by defining this function here, we just gave Prolog a couple branches to check for some provided list, right? So the depth here will be like how many numbers are in the permutation. If we look back at the tree here, the depth is related to the depth of the tree, right? And can you see the correlation between the depth of the tree and then how many, the size of our permutation, basically? So we need to specify that, and I just did so using a depth parameter. And when the depth is 0, this builder here is going to be like our, like a temporary list that we keep adding to. And then when we're happy with an answer, we bind it to solution. So builder will be like our scratch work. And it's going to change depending on the backtracking that's kind of going on. And then when we finalize it, we just bind it to solution. So this line is saying is just basically giving us one particular solution. So whatever the value of builder is, we bind it to this is a stand-in for solution. So they're going to equal each other. And so we have found a packing is what that's saying. And the depth would be 0. So it's going to use pattern matching. And whenever the function has a depth of 0, we're going to bind to that list and it will behave like a base case. So notice here I'm checking that the depth is greater than 0, which is good. And then I'm calling the iterator function. And the first thing that it will try is the x will be the first value of the list. And then it's going to continue calling subproblems with x. And then when it tries to backtrack, like if you're not happy with the solution, it's going to try the next element. So pretending that we have some value of X. So let's say, let me change the, have some value of X, like let's say the first element. What we're going to do is our scratch work, our builder parameter, we're going to add it to, we're going to add that element to it. So maybe bag will be empty, and then we're going to append the value of X to it. So our bag will be this, or sorry, the builder will be this, and then we decrease the depth and then call the subproblem. So depth and the first call to this depth is going to be, new depth is going to be if I guess, okay, let me explain it this way. So our call, I'm just going to do 1, 2, 3 for list, and depth originally initially is going to be the size, which is 3, and then so a new depth here is going to be 2, and then we call this problem. So we're passing in the bag plus that element. I want you to notice that, and then we haven't bound yet. We're just decrementing the new depth. And next call, we're gonna again force iterator to pick an item from the list. And this kind of mirrors the this tree here. So at each decision, where the pool of items that we're gonna look at is just gonna remain the same. So we're just gonna be making the same decision on the same list over and over again until we have a depth of 0, in which case we bind. So notice that I'm not changing lists, right? So let's just step through this and see what happens. So we're going to give it a pool of items 1, 2, 3, like I said, and then builder is going to be empty, and then bag is the thing we're interested in, and we're going to pass in the size for the other parameter, which in this case is 3. All right, so builder will start out as being empty, and we haven't bound to the very last variable, meaning that we haven't found the solution. So it's going to check the depth, okay? And then iterator is going to bind to the very first element, and then it's going to add it to the builder, and then okay, so our builder is going to go from empty to having one element, and then we're going to check the size. We're going to recursively call the subproblem with a decremented depth, and so we're going to make the same decision again and just choose the first element, because iterator is always going to traverse the first element every recursive call and then move on to the next. So you can see that the first path is going to produce 1, 1, 1, right? So we have 1, 1, 1, and this corresponds to, at each decision, we just choose the leftmost element in this tree. So imagining instead of C, B, and A, we have 1, 2, 3. We're just going to choose 1, 1, 1, 1, 1, and then we backtrack. And in our first time we backtrack, when we have C, 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 we backtrack and then we try, iterator is going to go on to the next value. But bear in mind, at this depth here, we've chosen C and C. So instead of C, we're going to try B, and we get C, C, and B. Does that make sense to everybody? Okay. So, yeah, that's backtracking. And basically, we're just modeling this. All right. So as far as the project is concerned, we don't just want, these here are all the permutations, but is it guaranteed, if those are placeholders for item weight pairs, is it guaranteed that they're all going to be valid? No, right? Because we don't know the weights. So we have to find some way to prune this tree so that it always stops and binds to the optimal packing. So let's look at the first observation that we have. Okay, let's just imagine that we have, I'm going to assume that we have built a list of certain items up to a point, and now we're forced to make a decision, right? So we have items A, weight of 9, B, weight of 9, and then the pool of items that we have to choose from is C, D, and E, and the total weight is 32. but the remaining weight that we have for the, anyway, it's a little better. The remaining weight that we have is 14. So we have, our iterator right now is just stepping through all the pool of items. But one, that's not efficient and it doesn't really help us in finding an optimal packing. So if we know the remaining weight, is it necessary to traverse through all these items? Our bag has a remaining capacity of 14. No, it's not, right? Which item is not necessary to iterate through? Right. And the reason why is because its weight is 15. So if we try to pack that item, then it's not going to be an optimal packing. We've exceeded the capacity. So C and E are our only valid branches that we want to check. So consider our iterator just goes through all the elements. And then when you define the remaining capacity, then it's going to restrict our pool to certain items, right? So that's the first step towards making the algorithm more efficient and also optimal. So another thing is I mentioned without replacement, right? The way the code is it can do duplicates, right? Our iterator, if our original subproblem picks one for the iterator, our original problem picks one, and then we call the subproblem, our iterator is going to start at one again, and one, and one, and one. So it's actually going to allow duplicates. So another thing that we have to worry about is if we pick an item, should it remain in the pool? No, right? Without replacement means that we have to start a new packing for us to consider it again. So let's say that we pick C, then in the next subproblem, our pool is going to shrink, right? Because we can't pick C again. And when we select this, we put it in our builder. We put it in our builder, and then we adjust the remaining capacity. So originally it's 14, and because we added this item, we're going to decrement the weight. So 14 to 12. And now our pool is D and E. Unlike our code is just going to think, oh, our pool is C, D, and E. I'm just going to call a subproblem. It's going to be C, D, and E. Okay, so that's another way that we can prune this tree. And then if we pick D, then our remaining pool is just going to be E. And because we can't pick C and D again. So we adjust the capacity from 12, we go to 8. And then we pick the last item, which is E, our only choice, and it happens to be feasible because it's less than our remaining capacity. We add it to the list and then we decrement weight, and then we have 0. Is this an optimal packing?
You go full. Is that just another item?
D. 15 to 4.
It's size 15, so we ignored that.
Oh, sorry. So this was, I changed this example a little bit just for illustrative purposes. But imagine that this is just 4. This here. So I was just covering a case for that. So imagine this was 4. This was absolutely a mistake on my part. Okay. Okay. So imagining that D is 4, and I think it'll say 15 because it's like an animation, but D is 4 at this case for the remaining steps. So we pick D and then we subtract off the weight and then the weight becomes 0. And then this is an optimal packing, right? We physically can't fit anymore because our remaining capacity is 0. So even if we had a list of items to iterate through, it doesn't matter. This is a solution. Okay. So yeah, that's 15 here. I forgot to change that. Okay, so another thing, yeah.
If, let's say there's like one remaining weight, but there's no items that are, like all items remaining are larger than weight one.
Yeah, I'll talk about that case. Thanks for considering that. So the question was, if we have a remaining weight of 1, and then all the other items are greater than that, what should happen? So that's something to keep in the back of your head. So when do we have an optimal solution? So maybe you might think that when the pool is empty, or when the remaining capacity is 0. And those are like reasonable assumptions, but we want like the broadest, most general case for this project. So if we consider an empty pool, okay. So if we consider an empty pool, this is a counterexample to that. This pool is not empty, but the remaining weight that we're at is 1. So exactly as he mentioned, none of those items fit, even though it's not empty. So if they're all invalid, it might as well be an empty pool, right? So this is just checking for an empty pool is not sufficient. And so if you're checking for 0 remaining capacity, what about optimal packings that don't deplete all the capacity? They are possible. So if we look here, I changed this example up a little bit. Our remaining capacity is 5. And then the last thing that we have to consider is an item with a weight of 8. So we can't possibly add that. This is an optimal packing. So what's the solution? So basically, in a broad sense, of all the available items, if you can't find a feasible item to put in your back without while remaining within capacity, then you've reached an optimal packing, and we just bind to that. Does that make sense? So we're not looking for an empty pool. We're not looking for a 0 remaining capacity. Just of the available items, can you physically fit any of them? Is our base case to bind. Okay, so some hints: submit a self-contained file and then sort your final solution list because that's how we're going to grade your solution. Your recursive calls might be in a different order than ours, and we don't want to penalize you for that. So if you sort it, we get all the items in all the right places. And then consider the functions member and delete might be helpful as well. Think about how you'd use those. And in general, this find all is your best friend. So if you find like some, I don't think I actually went over that. Okay, so I'm gonna stop the trace here and the debug too. All right, I'm gonna iterate through this without a trace. So, oops. All right, I'm gonna test out this perm function. We're gonna give it a pool of 1, 2, 3, and then builder will start out as being empty. And then remember, this is a scratch pad. When all the variables have been bounded, this is when we found a solution, and Prolog would return you a value. And solution is our item of interest. And then the depth we have to pass in the list, the size, in this case 3. Okay, so as the name suggests, it just gives you all the permutations, right? Okay, so you've just defined a function that gives you all the permutations. And let's say a simpler version of the project, it wants you to return just all the permutations, not considering the weights. So this is where find all is going to come into play. So provided you have a function that's expressive enough to capture multiple solutions, your find all is going to call that function over and over again, and then append each of the solutions to a bigger list. So if I call find all, or not find all, I've defined a function all perms, which is going to take a pool, and then our item of interest is a list of all the possible solutions from our perm function, and we just have to pass in the size because that's how I defined it in the perm function. We need to specify the depth. In my case, it's the size. So find all, and then assume that perm is given this pool, and then this is the builder variable. And then it's gonna cur, when I called it here, cur is a stand-in for x, right? And x is one of our solutions. So this is gonna be, if we call it once, we get a solution. If we backtrack, we get another solution. So cur is just gonna be a placeholder for one such solution. And then in our find all, we put it here. This is the thing that we're interested in. And then a thing to bind to. So for each one of these, it's going to be called cur, and we're just going to append cur to lists, which is our list of solutions. So each one of these is just going to be in a big list. So find all, or not find all, sorry, all perms, pass it a pool of 1, 2, 3, And then this is what we want. And you can see that it binds to a list of all the possible solutions. So in short, if you have a method that gives you multiple solutions, find all just appends them all together. Is anyone confused about find all, any of the parameters? Please ask. No? Okay. Um, remaining hints. There has to be a better way to do this. Okay. The next thing is pattern matching. So remember, if you are given some list, you define a function, you can access the head and the tail. Well, in this case, we have a list of item value pairs. So the head is going to be a stand-in for what? What is the head of a list? So yeah, right, exactly. So the head is like, imagine popping an item from a list, the head is going to be that value. So you can make your pattern matching more expressive by specifying that it'll be an item value pair. So in some method, you could say, I'm provided a list. I know the head is going to be item underscore val, and then the remainder will be all the other item value pairs that exclude the head. And then you have access to the current item value pair that you are processing. Does that make sense to everybody? Okay. And then we strongly suggest that you complete and understand homework 8. Use the parser to write your solution for the project and just like understand what the recursion is doing. As a challenge, I'd suggest taking the permutation file and maybe just having all the permutations except all the numbers are even or odd or something like that, and then trace through it and then see how the backtracking works out for that. And then it's worthwhile to spend additional time just practicing with this language. I think that like 90% of the challenge with this assignment is one, comfort with the language, and two, recursion. Like I said, it's like 10 lines. If you know what you're doing, 30-minute project tops. And then if you need like more resources for like how to like Prolog examples, for instance, use the official Prolog site, look through the examples, read through that. And then if you still need help with backtracking, this video here visualizes backtracking for the n queens problem. It's a really good watch. It shows you like how the recursion is unwinding for a different problem, but I think it's good for intuition building. And cuts. Cuts there, I think some TAs have a solution with the cuts. My advice on that is that you don't use them. They kind of interrupt execution flow, and they usually are like a tell that maybe you haven't covered all your bases with your edge cases. So you want to create a tree that a recursive tree that naturally progresses so that you don't need a cut. And a cut, what it does is you could say like for this particular method, I don't want you to do any of the backtracking. So that's kind of janky, right? It's best to just come up with clean edge cases or base cases, and then just have your tree be natural, not needing any sort of interrupts. But if you notice that maybe for your project, you're backtracking too much, a cut might be a solution to that. But like I said, it's hacky, so use it with care. I think that's everything. Yeah. No, don't do that. Are there any questions? Thank you, thank you. Seriously, are there any questions? Yes, yes. All right.